I have started, I think.
Acha, okay, thank you. So guys, welcome, and this is our third session on ROS tutorials in Syscon Talks, and today we will see or look at navigation. We have already kind of got introduced to this idea of controlling the Kobuki robot. Now we will see how to properly make it go from one point to other and add some intelligence to it. So this is the overview, and first we'll talk about how to in general move the robot, the Kobuki base, between 2 points A and B, and then we will consider a case where the path has an obstacle, so the robot cannot just follow a straight line path and reach the goal. So in that case, what we can do, and what feature of gazebo can help us in navigating around an obstacle. And then finally we will talk about a algorithm which will help us get past the obstacle. So let us take a look at what we have already covered. So we covered some concepts, and then we covered this control of Kobuki robot. And to control the Kobuki robot, we earlier saw we need to deal with these two topics. So these first topic was odometry, and the second was velocity, which was accepting a twist message type. So odometry is like a topic which will provide us data, so we have to subscribe. And then the velocity is a topic where we have to publish data, like we need to publish commands. Okay, so last time we saw how to control robot programmatically, and these two files are these two snapshots are from the last time. So in the snapshot which is to the left, what we are doing is we are getting the odometry information. So if you see line 26 there, we are creating a publisher, sorry, we are creating a subscriber uh, which is going to accept this odometry data. And in the snapshot which is to the right, we are creating a publisher in line 10, and this publisher will help us uh, send velocity commands to the robot. Okay, so in line 13 and 14 in the right snapshot, we are setting some pseudo values for linear velocity and angular velocity. So this will make the robot go in circles, and I hope you have tried this at your own time. So let us take a look at uh, what's going on behind the scene in ROS graph. So basically, when we are running our publisher and subscriber, which was just shown now, you can see this Kobuki test drive topic comes up, and this test drive topic is publishing to this velocity topic, right? And then we have this odom message which is being subscribed by our log position node. Okay, so let us just go and verify the name. So first name is log position for odometry, and then test drive Kobuki here. So if you see, the node name is test drive Kobuki here in line 7, and here the node name is log position. So all is in order. We verified. Okay, now let us talk about how do we tackle this problem of making the robot move from point A to point B. Okay, so to do that, here is a conceptual layout, and in this conceptual layout what we have done is we have abstracted the robot Kobuki as a just composed of two topics. Okay, so these are just two topics. One is like a velocity topic and one is a odometer topic, and we have already seen these two, so nothing new here. What is new is this goal type and this point message, and then there is a controller. So what we are going to do essentially is we are going to create a new node, and this node will be called controller node, and this node will do three things. First, it will accept odometry messages. Second, it will accept point messages, and thirdly it will publish twist messages. Okay, so there is a reason, what we essentially want to do is we want to tell it a point or a goal location, and then we want the controller to take care of making the robot move. Okay, so this is the conceptual layout, to simplify this whole process. um, so let us go ahead and implement this. So essentially we will need to implement a controller logic. Okay, and that controller logic is written here in equation 1. So before that, let us just do some ticks, like, or check marks. So first check mark is subscribe to ODOM. Okay, this we have already done. Publish to velocity, we know how to do that. Subscribing to goal, now this is something new, but this is just like a regular subscription, just that we need to know what kind of message we are subscribing. So this goal will have geometry message type point. Okay, so point message is defined in geometry messages, and we need to import that particular definition from that particular library. Okay, so geometry message will give us point, and then what we need to do is we need to compute this control action. So control action was linear velocity and angular velocity. So we denote this linear by v, angular by w or omega, and then here is our control law that we are going to do. So this is nothing but just proportional control law. Here there are some new symbols k1, k2, d and e. K1, k2 are just positive constants, and d and e denote distance between the 2 points a and b, and e denotes the angular difference between current and desired heading. So this heading might be a new term, and heading just refers to the direction to which our robot is pointing. So if, like, so heading is always relative, right? So whenever a robot is initialized, so at that point, if the robot is pointing somewhere, that becomes its initial heading, and that is kind of a reference, like a 0, and then we compute we calculate heading with respect to that particular reference direction. So it's in gazebo we get this reference as the positive x-axis. Okay, so usually that is how we take it, but like we can like in our robot Kobuki, what happens is this sense of direction and position, this is internally calculated. So what happens is, suppose I start my robot at some location with some random heading. In that case, my robot's internal heading will always be like it does not know about what is the positive x-axis of the world. Okay, it will just keep its original heading where it started as the reference heading. So okay, nothing much to be getting, to get confused here. What I mean is, Kobuki is internally calculating its own heading and position. So wherever you start it, let us say you started at the origin of the actual world, fine. But if you don't start it at the origin of your actual world, which is like the real position, then it won't know where it started. Okay, it will only start accumulating its or calculating its distances and angles from where it was initialized. Okay, so to actually deal with this kind of thing, we have this concept of frames. Okay, so probably Deepak will talk about it later. So we say that the robot frame refers to the location, robot frame is basically this reference where the robot starts, and from where it starts calculating its heading and all. Okay, so there is this concept of world frame and robot frame. Okay, nothing to be get confused here. Okay, then what is this new topic goal? So I have already explained, like, goal is going to a goal is going to be a topic which will help us tell the robot, okay, what is that point we want the robot to go to. Okay, so that's what it is. And here is the definition for goal. So goal is just a point type, and point has three members, x, y and z. So we will be using x and y because our robot is based on a plane. We won't be using z. Now this is the controller template, and a few things to note here, first of all, we have to import these corresponding things. Like point I have imported from geometry message, and then I am importing some mathematical functions from math library, and then there is this very important concept of global variable. So what is going to happen is, our controller is a Python script, right? And in a Python script, what happens is, like, there is a concept called scope. So scope is basically uh, like you know scope is basically the area, or like you can say it is basically the context where a variable exists. Okay, so if I define a variable inside a function, then the scope of that variable is limited to inside that function. So once you come out of that function, that variable vanishes, or it is be erased from the memory, or like you can say it is released, the memory is released. Now what happens is, in our script we will receive some data like post data which is required in some other function. So see, this callback is one function, and then this loop is some other function. So these two functions cannot talk directly to each other. They can, if this function is going to call that function, it can pass a value, and then if it is going to receive, it can receive. But the thing is, like I pointed in the first session, in robotics what we want is like these concurrent things, or like asynchronous programs. So basically this callback function, its execution is not controlled by us, but it is controlled by ROS, right? So whenever a message is available, is made available, then this function is called. Okay, so we do not control when this function get called, but it is called by the message or the topic. So whenever there is a message, a topic will call this function and give us the data. Now this function will asynchronously execute. So what happens is, we cannot get the data here directly, by calling, because we are not going to call. So what instead we can do is, we can use global variables. So global variable are those variables which have scope, which have like a global scope. So global scope means all the functions can access these variables. Okay, and then further, to discriminate whether we want to refer to a local variable or global, we have to tell inside each function about like what this variable is going to be. So this variable, when I write global, it makes it explicit that we are talking about the variable with the global scope, and not a local variable with the same name. Okay, so this is important, that you write global here. After that, this is the part where our application logic will come. Okay, so apart from that, there is nothing else here. Again, like we have defined this global, and we have set these scalar values k1 k2 that we will use. And let us go ahead and see what this application logic will look like. Okay, so once we are inside the main loop, so here if you remember, like, so I have expanded this particular section. So while not ROS Pi is shut down, so here, so this is expanded. So what we are doing here is, first we have this control, if control. So this control will check whether these two things exist. Okay, so what I mean these exist is, like, these should not be empty containers. Okay, so if you don't have a goal point, there is no point in trying to compute your control, right? And suppose you don't know your robot's location, then also there is no point in trying to compute this control. So once you have these two data fields, then it makes sense to compute the control. And then, so we just compute this d. To compute this d, if you remember, this d is that capital D in the controller. We need this dx and dy, which we are calculating here. And then we are calculating the current yaw. So this current yaw is basically your heading, so where your robot is pointing to. Okay, and then where is that point? So the goal point, like, at what angle is that goal point? So basically here we are calculating these 2 points, these 2 angles, and then we are calculating the difference between these 2 angles. Okay, so this difference in these 2 angles is your error in heading. And then this error in heading will help us to find out this omega. Okay, and this is your simple control law. Here I have one additional cosine term, like, so this was not in the control law. So what happens is, when you add this cosine term, your robot motion is kind of more smooth, because v is not only dependent on distance, but it is also depending on this error. So suppose your robot is pointing in the wrong direction, then you don't want to go very fast. What will happen is, you will miss your target. Okay, so this ensures that your robot, when you have very large heading error, you don't move very fast. You only move fast when you are pointing in the right direction. Okay, so this term kind of is very intuitive. Okay, and then we just compute this v and omega, and these v and omega. Now there is one more thing. So if your v and omega is very high, what happens is, your robot wheel can slip. Okay, so when robot wheel slips, what happens is, robot's internal odometry estimate will become erroneous. So what I mean is, like, robot will believe that it is like moving very fast, but actually the wheel will be slipping and it will be moving slow. So this will happen if your V and omega is high. So here I have applied a saturation block. So in this saturation, what we do is, if our V is greater than 0.25, we limit it to 0.25. Similarly, if our omega absolute value is greater than 0.25, we limit it to like plus minus 0.25. Okay, so this copy sign function is there to copy the sign of W and copy the sign to this magnitude. Okay, so this is how it works. And then, okay, sorry, my bad. So this is our application logic, and once we have implemented this, our robot will be able to follow a point. So just a recap. So what we will do, we will just publish our goal location, and our robot will just follow that goal. Okay, and this is the control law, and this is our logic. Okay, so once we are done with this, we have implemented our control law, and now let us say, like, you know, what happens when there is an obstacle in the robot path. So let us say, like, our robot is here at 0 0 0 and it wants to go to somewhere here, or maybe like it just wants to go between these two boxes, like somewhere here, or like, you know. So what happens is, it will, as it tries to move, it will be met with this obstacle, and then, like, if this obstacle is rigid, our robot will not be able to make any progress. So in that case, what can we do? So what can we do is, like, intuitively obvious that we need some kind of sensing ability, and that sensing ability will give us an idea of, like, whether the path in the front is clear or not. Okay, so whenever there is an obstacle, we want to know, like, whether path is clear or not. Okay, so obstacle is there, that means path is not clear. Okay, so to do this, Gazebo actually provides us some plugins. Okay, so plugins are the way out. Okay, so what we will be doing essentially is, we will be putting a 2D laser sensor on top of our Kobuki robot. Okay, so this use of sensor on Kobuki, this will, like, you know, this is made possible with the help of this something called Gazebo plugin. Okay, so let us talk about plugin. So basically, what is Gazebo plugin is that it is kind of a driver. So driver is like a software code. Okay, and this this driver is actually integrated into Gazebo, so it is able to provide us internal information. Okay, and we know that Gazebo already does this simulation, and it has all this information, so it can actually simulate, like, different things. Okay, not just sensors, but like, first of all, it was not that we started with a sensor, we started with this robot, right? So this robot was like a physical body or a rigid body, and then there was this cardboard box, which is another rigid body. Okay, so first of all, like, we use Gazebo to simulate this physics. Okay, so one type, so plugin, like, there are different type of plugins. So one of them is a model. Okay, or a model plugin or a physics plugin. So this plugin is actually what allows us to create robots in Gazebo. Okay, so when we say, like, a robot model, we are referring to a URDF model. Okay, so URDF is a name, like, it is what is referred, like, it's kind of a definition file. So URDF stands for Unified Robot Definition File. What it stands for is, like, it's kind of a description language. Okay, so for example, HTML is a markup language, right? So if you want to describe how a web page should look like, you use HTML. Similarly, if you want to describe how your robot should look, or like how it should be, like, you know, as a rigid object, then you use this URDF. Okay, so there are other specifications, or, like, you know, definition files, but ROS uses this URDF, so we are going to use this URDF. Okay, so in this model plugin, the model plugin allows us to define these these members. So it allows us to create links, it allows us to create joints, collision properties, and then sensors. Sensors in itself is another, like it has a bigger categorization because it is in itself a type of plugin. Okay, so basically what we see here, our Kobuki robot is nothing but a collection of these things like links, joints, and some collision properties. Okay, so there will be like so 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 in actual, when we are like creating a robot, what we do is like we create a body, then we connect wheels, and like wheels are not connected directly to the body of the robot, but is connected through something called a shaft, and the shaft allows you to have like this rotation or the motion, like, you know, so this is called a joint. So this second thing is joint, and then the third thing is the collision, which is like the which gives the hardness, or like, you know, the rigidness. Okay, so that's what a robot is composed of, all of these things. And then we have something called like sensor, which I already talked about. So there are like various types of sensors which are supported by Gazebo, and we can simulate them directly. Like, you know, there is a very easy to follow tutorial which is available here. So here you will find all the information about these plugins supported by Gazebo and how to use them. Okay, so the third type of plugin that I didn't talk about was the visual plugin. So basically there is one thing like which is the model of the robot, and there is one thing which is the visual representation of the robot. So here if you see this robot, so this robot looks like okay, my bad. So this robot, okay, I'm not sure where I'm going. Okay, here, so this robot looks like it has a body and all. Okay, but actually if you see the physical representation, like in the terms of rigid bounding boxes, it won't be like this. Okay, this is just the visual representation. Actually the rigid part might be a bounding box. Okay, so this visual rendering is a very important feature of Gazebo. Okay, it allows to do like, you know, visual sensing and all. So more information is there, of course. And then let us talk about how do we add a laser scanner. Okay, so first of all, we don't want to modify the existing Kobuki files. Okay, so Kobuki files are something which were inbuilt or which came with the Kobuki package, Kobuki ROS package. So we don't want to touch those. So without touching them, what we need to do is like we need to create some extra model properties. Okay, so just like I said before, a model is composed of these things called links, joints, and then your boxes, this rigid or like, you know, collision properties. So what we are going to do is we are going to create this description directory. So first of all, like this is our Kobo control project that we had earlier created. So we are inside this Kobo control project, and now we already have this controller py script and these launch files and all. So we are going to create a new directory called description, and inside that description we are going to create two more subdirectories. One will be meshes, one will be URDF, and this meshes directory will have this DAE file. So this DAE file is basically a visual element. Okay, so DAE stands for I don't know what it stands for, but it is called a collada file. Okay, so collada is a file format that is used to represent this mesh grid or like a 3D object mesh. So I did not create this file. It is available from the same link that I shown you earlier, the Gazebo link, and I just downloaded it and placed there. And then later in this URDF directory, what we are going to do, we are going to create this three important files are there. So first is this Gazebo file. Okay, so this Kobo underscore, so Kobo underscore is common in all, so just neglect those. Just this file is called Gazebo. Okay, and this file is called robot, and this the other file which is called robot without mod. So you can just ignore this third file, it is just usual file. Important file is this Gazebo, robot, and the mod. Okay, so this robot file will have the description of the robot, and this mod file is basically the file which contains our modifications. So let us go ahead and take a look at this mod file. Okay, so this is our mod file, and in this mod file what we have done is we have defined a joint, if you see here, and this joint is called Hokuyo joint. So this is how we create a URDF file. So it is just like an XML file, like we already saw this XML file when we created ROS package. Okay, so this XML file will have this like parent child hierarchy. Okay, so this tags, you are already familiar with this. Now what we have done essentially is we have created a joint called Hokuyo joint, then we have created a link called Hokuyo link. Okay, and then in this Hokuyo link we have defined this visual tag. Okay, inside this visual tag we have passed on the location of our DAE file. If you remember that Collada DAE file, this is the DAE file, so it will help in the representation of this. So the visual appearance will come from this Collada file. Okay, and then so this is the major part, like we create a joint and we create a link. Okay, now there is one very important piece of information, which is this line 8. So in this line 8, if you see this new joint will be created, like, you know, so a joint will always have two parts, right? So I mean, it needs a joint always exists on a foundation or a basis. So this the base is going to be this link called base link. Okay, so there has this thing has to exist. Okay, so what happens is when Gazebo tries to load this robot definition file, it will look for this base and then it will add this joint on top of that base. Now interestingly, this line 8 is actually what connects this modification, this new link and this new joint to the actual to our Kobuki robot. So basically the Kobuki robot has this link defined. So this link is already defined in Kobuki. I'm just calling it here. So basically what will happen is this particular joint will be placed onto that Kobuki link. Okay, and then our objective is achieved. So what we wanted was to place a new plugin. Okay, so this is just a model file. Okay, nothing like plugin here. So here what we have done is we have just created a joint, we have created a link, and this link will contain our sensor. Right now we have not added that sensor, we will do that in the Gazebo file. Okay, so the Gazebo file, it like, you know, if you see line 3 here, I am actually referencing that Gazebo file. So this kobo underscore gazebo.urdf. So this Gazebo file basically uses then this particular link. So let us recap. Okay, what happened? So our Kobo robot has a link called base link. Just like we have this link called Hokuyo, the Kobuki robot defines a base link. Okay, so we are going to place this new joint called Hokuyo joint, which is a fixed joint, on top of that base link, and then on this link, now this link will connect our base link and our Hokuyo, and Hokuyo link will contain our sensor. Okay, and you cannot see beyond line 30, but there are more lines, and then those lines uh, are just like this link only. Okay, so there is this inertia thing and then it ends, there are not many lines. So importantly, this Gazebo file, it accesses this Hokuyo link and then it adds the particular sensor there. So the sensor related information is inside that Gazebo file. Here we are just defining the physical model parameters. Okay, so this is our modification. So to do modification, we just added a joint, fixed joint, and then a link Hokuyo. That's all. Now let us look at this robot file, like the third file which was there. So in this third file, what happens is first we load the actual Kobuki definition. So the actual Kobuki definition is stored somewhere in Kobuki description under URDF, under Kobuki URDF Zacro. So Zacro is just a file name extension. It's eventually a XML file, and then this is the interesting part where we are including our own modifications. So this is our mod file, and then once we are done with this, and we spawn our robot, we will see this. Okay, so we will see this when we spawn it. Now this laser, okay, so this laser sensor, it is like we saw that like it looks like a physical thing, but what we are interested in is the data. Okay, so the data, the laser scan will generate some kind of data, and that data is defined in this sensor messages package. So this sensor messages package has this laser scan data type, and this message type. Okay, so our laser scan, so okay, so first thing is a new topic will appear. So earlier we did not had this laser forward slash scan topic, now we will have it, and then this topic will contain this type of data. Okay, so this data looks like this. So this data has a header, then it has a minimum angle, maximum angle, then it has an angle and increment parameter. So so there is if you see, like it is going to contain a lot of like these numbers, and it's a bit complicated. Okay, so it's not that ready to use, but it's like that. Okay, so this is how it looks, this is the type. Now let's go back to detecting the obstacle. So here we see that we have these lots of numbers. What are these numbers? So basically these numbers represent the radial distance. Okay, so you see some of these lines say INF. So INF is short for uh, uh, infinite. Okay, so but you know that infinite means nothing. So so here like in context of sensing, infinite just means that there is, like, you know, there is no obstacle along this particular like radial distance. So there is a formatting here, like in the way like these numbers. So how do we understand the meaning of these numbers? So these numbers represent radial distance along certain angles. So that angle is actually that angular span, like, you know, so the best way to understand is from this image. Okay, so this image, in this image we see that this laser sensor is kind of a sector. Okay, so sector is defined by this lower angle and then higher angle and then these individual scans. Okay, so what is happening is like a laser is being sent in each of these directions radially, and then it returns back, and we know like, okay, like what is the radial distance after from where it was reflected. So so that is exactly the same information which is represented here, like this is in meters. So what it is telling us is like in certain angles it is infinite, in certain angles it is this. So to find out the angle information, we need to use this angle increment parameter. So the first angle is going to be minus 1.57. So it starts from there. So the first reading is actually the reading or the radial distance at this particular angle, and then the second reading will be this angle plus the increment. Okay, so this is negative, so it will become smaller, and then after this, so this second reading correspond to this plus this angle, and then let us say nth reading. Okay, so nth reading will correspond to this plus n minus 1 times increment of this angle. So that's how you actually interpret the sensors, the laser scan. Now for our obstacle avoidance, we don't need such a finer resolution. So what we can do is we can just, like, you know, uh, take this increment as a very big value. Okay, that we can do, or we can just go ahead with this and just, like, you know, take all of these values, combine them and take like the minimum of them. So so there are two things. Okay, first of all, take all the readings in this angular span and treat them as a one reading. Okay, similarly do that for this particular angular span, and then do for this angular span. So eventually we have these three angular spans which are telling us the right, front and left information. Okay, so this is how you do that. So basically you create this laser callback, and inside this laser callback what you do is you convert your range data into just three numbers. So the first number is your data from like the last this has to be like let us say 5. Okay, so this is like 240. Yeah, this is like 240 readings. So you are taking the last 240 readings and creating this first angle, sorry, the first reading, and then you are taking the next 240 and then you are taking the last. Okay, so this is how you convert your lots of readings. So essentially for this particular example we have used the default setting. So the default setting gives you 720 readings. So the readings will start from 0 and the last will be 719. So we convert, or like we divide them into 3 equal angular spans, and this is how you do it. And eventually what we get is, inside this range data we will get 3 numbers, and these numbers will be representing what is the minimum distance along each of these angular spans. So we will know, okay, what is the distance, minimum distance in the front, what is the minimum distance in the left, where is the minimum distance the right. Okay, so that information is contained inside this range data variable. Okay, good to go. So far what we have done, we added a laser plugin, and we saw like what kind of data it gives, and then we tried to simplify that data, because that data was like a lot of data, so we don't need that much for doing a simple collision avoidance. So we just simplify, or like we minify that data, and we make it into a 3 representative variables, 3 values. Now going forward, how to use this data. Okay, so uh, next we want to talk about, like, how we are going to use this data to perform collision avoidance. Okay, so there is this algorithm called bug algorithm. This is like the one of the simplest algorithms to do collision avoidance. So this algorithm, what it does is it uses something called wall following behavior. Okay, so it uses this wall following behavior to navigate around an obstacle. So here is a representation. So if you see, this is the initial point and this is the goal, and there is an obstacle. So what your bug does is it goes in the straight line to the goal, and then once it encounters the obstacle, it will try to follow either a left wall or a right wall. Okay, so here it is following the left wall. Okay, and sorry, yeah, it is going towards the left, but it is following the right wall. So basically the wall is towards the right of the robot when it is going to navigate. So this is like right wall following behavior, and it will follow this obstacles right wall until it crosses the straight line connecting the initial point and the goal. So you see, it was going in straight line. If this obstacle was not there, it would have moved like this. So whenever it reaches a point which intersects with this straight line joining the robot and goal, it will again start moving towards your goal. Okay, and that's the wall following behavior. And let us talk about what changes we need to make in our controller in order to implement this bug logic or the bug behavior. So basically, if you remember our earlier template, so in our earlier template we had this velocity and odometry. Now we have the third topic called the laser, and this particular topic will give us laser scan messages. So our controller will have to accommodate one more callback or one more subscriber to this laser data. Okay, and then we okay I think I did not have this previously. Okay, so I created this another topic called goal status. So this, what it does is it tells us, like, whenever the controller has successfully navigated the robot towards the goal, we will publish a message and tell, okay, the goal has been reached, now can you give us like the next goal location, something like that. This is to complete the loop. Okay, so now our controller has to implement this bug logic. So what is this bug logic? So bug logic, to implement bug logic we need to understand these events. Okay, so the first event is uh, like the obstacle detecting, like, so whenever an obstacle is detected in the front region, okay, so that event we will use as a trigger for wall following behavior. Okay, so earlier our controller was just doing proportional control law. Now our robot cannot just do that. Okay, so what it has to do is something called a wall following behavior. Okay, And so the previous behavior is called goal tracking behavior, which was just like a proportional control law. Now what we are talking about is this wall following behavior. Okay, so what is going to you help in doing this wall following behavior is this second event called the obstacle detected in left. Okay, so we will use it for this wall following. So basically what happens is okay, so what we have decided is like you try it yourself, and then we have provided you the solution in Teams files. So first try to implement it, and then we will and then look at the solution. So but before that, let me add more about it. So basically there is going to be an event which will trigger these two behaviors. So the default behavior of your controller is your goal tracking behavior. So in this behavior what happens is your robot accepts a goal message and then a goal point, and then tries to navigate your robot towards the goal point. Okay, and then in between, following this behavior, what will happen is this event will be triggered. So whenever an obstacle is encountered, this event will be triggered, like an obstacle is detected in the front. As soon as this particular event is triggered, you go back to this wall following behavior. Okay, so this wall following behavior is basically like, keep moving your robot as long as there is a wall in a particular side. So here I have detected left, but this can be right. So in the example that we saw here, the wall was on the right of the robot. So essentially when the initially the robot is going to do the goal following behavior. Okay, so here it is going to encounter this event. So this event is there is an obstacle in the front, and when that happens, what you do is you rotate your robot right or left. Suppose you rotate it left, and then once you rotate it left, what will happen is the second event will get triggered, that is you detect a wall into your right. And once you detect this wall into your right, you keep following this wall. So this second behavior of keeping this wall following, this will be implemented how? So this will be implemented like, you try to maintain a certain distance from this particular wall, and then you just keep moving ahead. Okay, and then there will be a third event. Okay, so this third event, which I have not written. Okay, I think there will be a third event which is like you cross the line intersecting your like your straight line, and then your third event will be triggered, and then you will follow that particular you will go back to your original behavior of goal tracking. Okay, so this is how broadly these behaviors are implemented, and we want you to try this because it is a lot of theory, and uh, there can be like a lot of like little bit technicalities. So just try it, and we have provided the solution to you. And so I will stop here, and I'll hand over to I'll ask Deepak to take from here.
Uh, Hello, am I audible?
Yeah, hey Deepak, yes, you are audible.
Okay. Okay, guys, any questions so far from whatever Vivek presented?
Yeah,
Okay, okay,
I have one
Sushant,
doubt.
can
Yeah,
you be a bit louder one?
am I audible?
Yeah,
Yes.
So in the second session, you show that playground environment, right, where the table is there and Kobuki is running over the table.
Yeah.
So in that, if our obstacle is placed at the edge of the table and we implement this bug algorithm, so what happens if the edge comes and also the obstacle is we are following the wall? So what happens in that case?
Yeah, okay, good question. So, see, there are like two different sensors in Kobuki. So, I have not spoken about it, but Kobuki has something called a cliff sensor, and this cliff sensor actually helps you to identify these edges, these like, so essentially you don't want your Kobuki to fall from those edges. So that's why there are these cliff sensors. So,
uh,
here we
Vivek,
are not using the cliff sensor, right? But that yeah, tell me, Deepak.
yeah, I mean, like, as I was planning on running a few simulations, so maybe you can just show them the.
Sure, sure.
with the safe walker walai, I'll just publish the topic. That'll make more sense, I guess.
Okay.
Anything else? Okay. So I had planned on a few demonstrations. So I'll just share my screen. Yeah. We'll go. Okay, we'll start from the question itself regarding the cliff sensor. So that was yeah. Launch Kobuki gazebo. Playground, is it Kobuki? Playground. Launch. So you have the playground here. Let me just do this. Always on top. Okay. And first topic list. So you can see the events bumper and cliff. Now, I think if I publish it now, there won't be anything on it because the bot is not moving. So pub mobile base events. Yeah. Acha, sorry. I should have done echo, not pub. Yeah, it says clock is not published. Okay. So we'll launch that other file to move. Save random walker. So you have the bots moving. Now let me topic echo mobile base before it. Maybe. Yeah, it fell. Did it? Okay. Let's see. No, event. Cliff might be interesting. So ideally what should have happened is when it detected the cliff, you'll get state 1 here. Normally it will be state 0. You'll get a state 1 when it has come near the. Achha, this I guess is also, I mean, is there a lot wheels drop in this? Yeah, wheel drop. Let's try wheel drop. Okay.
So Deepak, this clock is being published. This message usually comes when, like, you know, your ROS core is not communicating to this.
Topic, right? I mean, the other this place where I'm echoing it.
Okay.
That's what you mean, right?
So
I'll see.
yeah, sure.
Background, because I tested it previously, and it was not publishing initially, and then when the vehicle started moving, it started publishing.
Okay.
So let me echo it beforehand. Bumper. Yeah, so I'm echoing it. Now I'll. So worker is there. See. So when it hit, you got the bumper 1 state 1. So that's how you can use the bumper sensor. Similarly for cliff, you'll get. And bumper also has these like IDs depending on the direction in which you hit. So it's sort of like a very short distance ultrasonic range sensor maybe. It'll also tell you along which direction you've hit. Yeah, so that is regarding the question. Anything else? If not, we'll start from the previous session Mallya questions. One of them was how to have multiple robots working. So you must have checked out the launch file, what Vivek put in his presentation, as well as if you had explored the package itself, Kobuki Gazebo, the standard launch files that is supplied, you should have seen them. So that usually has one portion which describes the world, and then the next portion which describes the bot, or the bot you're spawning. So for the bot part, I have modified a bit. So this world is still the same. So for bot, what I do is I put each copy of the bot inside this group. The font is visible, right?
Yeah, Deepak, it is.
It is visible. Okay. So bot 1, bot 2 are identical. In the sense, they use the same robot file. The robot name is different. And yeah, I had to modify a bit. So because by default, the Kobuki is sponsored origin. So what I'm doing is I'm passing this init pose argument to the robot launch file with like the appropriate initialization conditions that I want. So that's why it's still running the previous one. Let me stop that. Yeah, the killing part takes a bit of time. Okay. So ROS launch systalks multi. Yeah. Okay. Do we have any process running here? What is this? Achha, it's starting. Let me run it again. Yes. So you have one bot and you have another bot. So bot models, you can see bot 1 and bot 2. Bot 1 I had initialized at 10, 10, x and y. So like this is the origin. Yeah, bot 1 and bot 2. Yeah, like Vivek said, that the ODOM that you get is from your initial location. So now if I look at the topics that I have. So I have like one set of topics for each bot under the namespace. So when I put it under this group namespace, it'll create it'll create another level. It creates a hierarchy with another layer, upper layer, with that namespace, and then the whatever topics were there previously. So now if I check, so bot 1's initialization was at 1010, whereas if I check bot 1 SODOM, topic echo bot 1 SODOM, it'll give me zeros. So it's basically, I think last week I gave this wrong information saying this will give you the true state. So it's giving you the odometry. So odometry is a combination of both. Yeah, in this case, I think it's also using the IMU, but you can either have VLAN Kudos or the IMU or a mixture of the two. So Yeah, and if you want to get the real position, ROS service call gazebo get state. Yeah, I don't think have introduced services, but it's equivalent to topics. Services are a bit more involved in the sense it can be triggered, event triggered, whereas topics is something that is, I mean, that channel is open all the time. You publish or subscribe at intervals that you want, whereas services are event specific. So when I call for this model state, I'll get the model state back. I'll just confirm the model name, and this should give me, let's say, name part 1. Yeah, see. So true position is 9.99, 9.99, whereas the position that I get from ODOM is 000. That's regarding the what's published on ODOM. Okay. What can you do more with the laser scan and all these business? You don't need to actually start off from 0. So
Hello.
Yeah, good. Is that a question?
Does that mean that ODOM gives you relative position compared to original?
So once you move, it starts incrementing it based on your user location.
Okay.
Okay. So yeah, let's first look at some empty world. Let me just stop it. Yeah, we also have not discussed RViz yet, right? So let me just present that one as well. Let's launch. Okay, so before we get all confused, let me just zoom in on this bot. Yeah, so this is the bot that Vivek presented today. You have the same Kobuki mobile base with the Hokio scanner on top of it, and these are its basically a visualization of the scanning array. Now, okay, let's compare it with the conventional launch file that we were using so far. So what we did previously, we're launching this empty world.launch. So this is available in, I think, Kobuki Gazebo itself. Yeah. Sorry. Yeah, it's available in Gazebo ROS package. Sorry. So in Gazebo ROS, you have this empty world launch. Similarly, you have other worlds as well, which, I mean, for experimentation, you can use. You don't need to, you can create your own world like this, but I mean, for most reasonable problems, you have like so this is a model for an office space. You have these worlds with like random objects placed. So stuff like that is already available. You don't need to look for it. Let's just see what worlds are available. Gazebo ROS CD launch. So you can see you have the empty world that we're using before. the world that is launched right now is this Willow Garage world. So Willow Garage is basically, I think it's the guys who wrote ROS, their office. Is it right? Vivek?
Yeah, it was the origin place of ROS.
So, okay, now you have the scanner. What can you do with it? First, let's look at RViz. So ROS run RViz. So RViz is this visualization tool. Now, yeah. So now you just have the empty world here. You don't have the robot in Gazebo. I mean, the robot which is already there in Gazebo, you don't have it. So you add whatever is required here. Robot model. Okay. Now, by default, the description of this robot is named as robot description. But what I have done is I have used these namespace. Acha, so this is the other launch file. I'll open the corresponding launch file. Second. Here. So Kobuki with laser is the launch file that I'm using currently. Yeah, as you can see, Willow Garage world. We'll come down to what these are. Let's go step by step. So yeah, this is the part where I'm launching the bot. So as you can see, I'm using the namespace bot_1. So in robot description, I need to change this to bot_1/robot description. Yeah, you get the box, but still it's not the same as the bot over there. The issue then is to give the TF prefix. Yeah, there you go. It's all okay. So you got the bot, which is sort of behaving on its own, having fun. Yeah, we don't have the map yet. We have the laser scan. So to visualize laser scan, again, okay, you need to select the topic, bot1 laser scan. That's it. And you're done. Yeah, you can see the output of the scan here. The okay, maximize this. You can see the output of this scan. Okay, now you have the scan. Let's say this is an unknown environment. Okay, you don't know how you have the model, but you don't know the map of the model. Map of the environment. You know the environment, you don't know the map of the environment. So to build a map, you can use the G mapping that comes with ROS. So it's also an open source package which somebody produced. For that, what I'm doing is I have put together 3 different functions inside this launch file. So first, from Gazebo ROS, I'm launching the world. From my own package, I have the bot, which I'm launching at 00, spawning at 00. Then from this another package, Kobuki keyop, I'm also starting keyboard operation. So what I can do is I can move the bot. I'll go. Yeah, I need this window. So using arrows, I'll move the bot. Okay, so why teleop? Because in order to generate the map, I need to go throughout the environment. yeah, you can write an automated program like what Vivek just proposed. You can use the same bug algorithm, have the bot running around, but you need to have some sort of check to decide when it has covered the entire environment. So the algorithm that Vivek suggested today is to go to a goal location. So you can, I guess, randomly keep changing the goal location, and bot will go from one point to the another. And hence you can basically move around. Okay, why move around? Let's go back to the thing. So using this, you move around key op, and using the next package, G mapping, you're mapping the environment. Okay, these are the parameters for G mapping. You can just copy paste for now. It'll like, yeah, it does matter depending on your sensor, but since it's a simulated sensor and you don't have the hardware, so if you had the hardware, you could have changed this one. Yeah, you specify what is the robot's base frame. So our robot's base frame will be, as you can see, base footprint is the base frame. Then you need to specify ODOM frame. ODOM frame is bot underscore slash ODOM. And then the map frame. Map frame is something that you publish out. So like when I run this node, I'm getting a new topic called, I think, either bot1 slash map or just map. Let me check. ROS topic list. Bot1 slash map. So bot1 slash laser slash scan, Vivek already explained. Teleop is to control your bot via keyboard. These were already there, including ODOM. So you have map metadata, and slam G mapping entropy. So out of which map is something that you can use to visualize here. So you had robot model, you had laser scan, I'll add map. Same process, I need to give it the topic. 1 second. Yeah. So why this area got highlighted? Because it's free area, and the walls are colored in black. So as you can see, I'll just I'll just move it around and it will generate. Okay, I need to. Yeah. Okay. Apparently, I'm not very good at this. So as the bot moves, you have the updated map. Okay. So that way, once you have covered the area that you want, what you can do is use another standard package, ROS map server, and the function is not function. The node is map saver f, and whatever name you want. Let's I'll just call it test. Oh yeah, sorry. So by default, it takes map topic. So I need to remap to bot_1/map. Why didn't this work?
Colon equal to, right?
Oh yeah, sorry. Yeah. So let's see what we got. It's stored in home. So I have these two files for test. First of which is PGM, which is the same as this. So this is a portable. Yeah, I don't remember the full form, but this will be basically 0 and 1s, and I think the gray is 0.5. So you have basically 3 states. Like 0 will be empty, 1 is the occupied, and 0.5 is the unexplored. And yeah, don't worry about this size. Like it'll, if you had explored more, the size would have increased. And you will also get this parameter file. Resolution. Yeah, origin is something by default, which I think you can change. Yeah, but why change? Okay. Let it be. So yeah, so even if you're starting from 0, 0, the bot thinks you're starting from -10, -10. So that's okay, because henceforth, if you're going to build everything based on this map, the coordinates will be basically a shifted thing, and it's not the coordinates that you get from Gazebo. Okay, so once we got this, let's look at what the original Willow Garage map looks like. So I'll CD, I think it should be there in that Gazebo ROS. CD launch. Yeah, if not, I have it elsewhere. So yeah. So this is how. Yeah, this is taken from another, again, open source package. So they explored the entire area, and this PGM was created. Okay, so once you've got this map, what to do with it? Well, you can use this for localization. You can use this, basically you use it for localization and then do whatever. Yeah, you can identify dynamic obstacles. For example, you have this map, and then you have the scanner as well. So let's say something that's not there, I mean, some obstacle which is not there in the map, you can classify it as dynamic obstacle clearly. So that way it's useful. Let's, without saving. Yeah, the final demo that I planned on. Okay, I've got 10 more minutes. Was once it stops, obviously. I have nothing running. Okay, yeah, cool. So the last part, I mean, I tried to integrate it into the Kobuki itself, but due to lack of time, I couldn't. But let me show it using the turtle bot. Gazebo. Yeah. So I launched a world with some random objects. Yeah. So this is again, the base is sorry. Same as Kobuki. I think Vivek mentioned this previously as well. So Turtlebot is an extension of Kobuki with so they've got these sensors and all mounted on top of it. So if you notice a topic list now, so you have identical mobile-based topics which came from the same Kobuki base. In addition, you have this laser scan. You have this. Actually, you have camera as well on top of this camera, and that gets so there's I think Kinect also. So that depth image you can convert to laser scan. Yeah, interesting features. So that's Turtlebot. So I just launched Turtlebot right now. Let me launch. Let me also run the map for this. So ROS run map. So previously we had we used map server, map saver to save the map that we generated. We'll use map server to load the map. So map server, the argument is map file, and you need to give the path. I'm not sure. I need to check this, but let's go. gazebo/maps/playground. Yeah. So, okay, now you had, so when I created this test map, you had these two files, test.pgm and test.yaml. So you need to pass YAML here. What happened? Valid. Okay. Why? I do something wrong? Not before.
Deepak, just verify this file path is correct or not.
Yeah, here. Okay, I didn't have to specify the argument name. I didn't have to write map : equals. There you go. So map launched. Okay, let's again go to RViz and see what's going on. RViz is useful for any sort of visualization. Like, yeah, again, you need to set ODOM as the base. I don't know ODOM. Yeah, I have ODOM. Next, I'll add robot. Yeah, you see the robot. So right now it popped up instantly because the standard way to do is you are launching just one robot and there's no namespace business. The robot description is robot_description. So if you have multiple bots, then you'll have to change this robot descriptions. Okay, next, let's look at map. Where are you? Where are you? Here. Okay. Give the topic map. Array. No dot. Okay, I'm still getting an error. Why am I getting an error? Oh, I need to change this fixed frame, is it? Oh, it should have worked fine. Okay, let's try base footprint.
Hey Deepak, can you make that to map, that fixed frame to map?
It was on map. Yeah, the robot, it starts giving an error. And it is working fine. Maybe, yeah, the basic idea is just this. Huh. Okay, I'll check this out and post in Teams later. So it was working fine previously. Yeah, the idea is whatever you want to visualize, you keep on adding. Okay, now, so this is the same thing what we have done so far, right? What's new about this? What's new about this is, don't worry about these errors because it's just a visualization error. The simulation is running fine. And the next thing what we'll do is we'll launch this localization. Turtle board. Gazebo. So, oh, yeah, it's working. Yeah, again, ignore this for the moment. AMCL is adaptive Monte Carlo localization. So what it does is, so you have laser scans going on here as well. That's right, it's working fine. So you have laser scans going on here as well. Oh, no? Yeah, no bueno. It's not cooperating, fine. In addition to that, you have the map. So based on these two, the localizer is trying to estimate its position, the robot's position as well as heading. So, wow. Yeah, the best thing that could happen in a demonstration is this. Cool. Yeah, so ideally what you would have got here is a blob of vectors with each vector describing the probability of it being there. So all of those are sampled based on your localization algorithm. Yeah, this again, like maybe I'll record it and post it in Teams, the demonstration itself. Yeah, and in what topics do I have at this stage? I have so many topics. Cool, very rich. Out of which this set is the original one about the base, and these are the gazebo topics. These you can ignore. I mean, if you're not using them, camera and yeah, this is CMD well. Yeah, but you can directly use the robot base command / velocity to control the bot. Don't need to bother about this one. And then you have the ODOM. You also have, okay, I did launch a planner as well, which I have not tested, so I cannot say whether it will work, but let's look at the topic itself. So ROS topic, move base, sorry, ROS topic echo, move base, goal. Okay, nothing is being published. Let's try and publish something on it. Target post. I will make it 10 hours. Okay, I have 10. Let's see if it moves. No, I think 100. Pub. Wish. That's a goal. Oh, it's just okay. Yeah. Yeah, it's publishing here. Is it going? It's not yet going. Okay. Yeah, that's why I suggested on showing this. Yeah, but you have the inbuilt motion planner and controller as well, which is supplied with ROS, and so it's sort of compatible with different sort of boards, where you can change like the, I mean, differential drive, omnidirectional, bicycle model, or whatever it is. You can put in the appropriate model and you'll get it working. Yeah, this, I mean, we can do this navigation stack. Yeah, this entire process, the like mapping and then localization and these motion packages are everything clubbed under something called as navigation stack. So, I mean, we can create a follow-up session sometime if there's interest for it. But yeah, I guess that's it from my end. Yeah. Before winding up, any questions on this? Any comments?
I have a question regarding the Vivek's presentation.
Vivek, maybe you can.
Yeah, go ahead. Yeah, tell me.
Yeah. So there you use the proportional control, right?
Yes.
To control the board. So if I want to use the PID controller in a script, I saw somewhere that they use different kind of distances. So do you know about that? Like,
So you can use PID control as well. Like, I mean, so this was like a simple control law, right? Here, what happens is your V and omega are computed using just like proportional control. So you can have like an integral term, and then you can have a derivative term, and it's like it's just the same thing. Like, eventually you get a value of V and omega and you apply it to your robot. So the important point to look for is that your V and omega should not exceed those saturation values, because if they do, you will observe something called wheel slip, like, so your robot will report erroneous odometry.
but I saw there that they did not use the same error thing multiplied with all the constants. So that's what I was asking.
Perhaps if you can give us a link or something, we can look it up and then come back to you, like,
Okay, sure.
yeah.
And also, what's the difference between IMU and odometry data?
So IMU data, just like you can just like Google this IMU gazebo plugin, and you will see what all information it gives you, like, so by default, I like as such I don't think I have used IMU, but I think IMU will give you this position, velocity and acceleration, all three things. So just look it up. I am not really sure like what information it gives you.
Yeah, and also in most of the scripts, people use the Python class thing. So why is it so? I mean, it becomes difficult to understand like multiple self dot like.
Yeah, so eventually what happens is using classes now, like things become simpler when you use classes. You don't have to create global variables, like, so that's one advantage. Like, so learning class can be a little bit complicated at first, but if you just like, it's not that complicated. But what I'm saying is there is a little bit of learning. So once you become familiar with that class thing, that self dot this and that, it will be helpful. Like, it will reduce the complexity. So, one good thing about class is that it allows you to reuse lot of old functionality. Just do some inheritance, like, so there are these concepts like inheritance and all. So classes are very good, but without classes also you can do. So in our codes you see that we have not used any class, right? So
Yeah.
so definitely you can use without class, but learning class is a good idea, and it will help you, like it will simplify a lot of things.
Okay. And I also encountered difficulty in attaching like different sections in a simulation. Like if I want to add the world and I have the three files like controller file, world dot world file, and something else like let's say some data sensor data. So I'm facing difficulty in connecting all three in a single simulation. So can you
So
tell some simplified way to do things?
see,
You have
one
three different nodes,
simplification.
is it?
Yeah, Deepak,
Sorry.
say.
No, I'm trying to understand. So you have three different nodes which you want to connect.
Yes, yes, yes. But dot world file is it a node or I mean I'm not
No,
sure.
it's a world which you pass to I mean the launch file. So if you check out that launch files in either uh, the empty world launch file,
Mm-hmm.
that Kobuki underscore gazebo in the package, inside that you have Kobuki Kobuki empty, is it? Kobuki empty dot world, right? Kobuki empty dot launch.
Okay.
So wait, let me just share. Yeah, so this is the launch file that you're using. I mean, we were using previously, where the first part was to launch the world, and the second part was to spawn the robot, right? So over here, this is where you're specifying the world name, rather the world. So your world file goes here with the path.
Okay, so if I have custom dot world file, so I
Yeah.
have to just update this thing, right? Empty dot world thing.
Yes, you can replace world name with that path to that,
Okay, okay.
and it should.
So yeah, is it compulsory that it should present in the same package or some
No, no,
like?
no, no. So as you can see here, this is Gazebo ROS package. That's something else. What I did was I had a separate package which I created. That was something else. So this Kobuki Gazebo is some other package. You don't need to place them in the same package. It's just that you need to specify the path, proper path where it is located.
Okay, okay, okay. Got it.
So this is for world, and the controller node can come here, and sensor node can come below that. I mean,
Okay, okay. I got it now.
yeah. Uh, Sorry, I thought I wanted to add to the previous discussion. Yeah, the discussion on classes. So basic advantage is that your ROS is inherently like concurrently running stuff, right? So even if you have inside a single node, you have these callbacks for topics as well as services. I mean, okay, let's not touch services for topics. So the callbacks actually run independently from the script. So on a separate thread. Hence, even to manipulate data across two parts in a single script, you will have to pass arguments and return them like inside each function. So that becomes cumbersome if it's a long sort of script. Hence, you can use class. Yeah, I agree. Writing self everywhere becomes a bit involved, but yeah, it's a good habit to develop, I guess.
Yeah, okay. And also, like, if suppose I want to learn the navigation stack thoroughly, so what approach, like, can you Please tell something.
Okay, I'll just post a good tutorial on it. We can have a session, but given the response this one had, I mean, at least in the short term, I'm not sure, but let's see. This site is by KEST, if you know. KEST, I think Korea, right? Korea Institute of Advanced Science and Technology, I think. So they have given how to execute and get a navigation stack running, but how to use navigation stack, as in like specific parts of it, you need to get a bit. I mean, you need to get your hands dirty a bit.
Yeah, actually, I saw the ROS documentation for that, but it is quite
That's not
lengthy.
that great. Yeah.
Okay. So, is it helpful, like this Korean institute? Like,
Yes, you can. I posted it in the chat, so you can refer to it.
okay.
It'll at least tell you how to get it working.
Okay.
Anybody else? If not, over to you, Harsh.
Yeah, sorry, I was just not able to unmute myself. Okay.
Chill.
So thanks a lot, Vivek and Deepak. That was very wonderful series of 3 sessions on ROS. So thank you very much for your valuable time. So thank you everyone in the audience for joining us. So I think that's it from our side. So I think we can close the sessions here.